In this video, we're going to look at an important inequality involving infs and soups. To get started, we are going to let S be a set with both a supremum and an infimum. In other words, sup S and inf S both exist. Now it's important to realize that we know that S itself is not empty. So there is at least one element inside set S. And that's going to be enough to let me say that the infimum is going to be less than or equal to that little s, and that little s is less than or equal to the supremum. And in fact, this particular inequality is true for all elements inside my set S. But the fact that I have somebody in here means that I can now definitely say that when a set has both an infimum and a supremum, the infimum is less than or equal to the supremum. That is not a surprise, but it is worth making a note. But we can go a little bit further as well. What I want to note is that if I start with my basic inequality, that the infimum is less than or equal to S, and S is less than or equal to the sup, I can add things on both sides. The infimum itself is bigger than or equal to any lower bound for my set S, and the supremum is less than or equal to any upper bound for set S. And what this means is that I basically have the following kind of a number line. Here is my number line, and on this number line I am going to put the infimum of S there, and I'm going to put the supremum of S here. And what I know is that all elements of S lie between these two things. And I know, obviously, that all of the upper bounds are out here. The upper bounds include, they start with the sup, and they go out here. The lower bounds start with the inf and go out here. So the lower bounds are all out here. This does not mean that S is an interval, but it does mean that the set S can be trapped inside a closed interval. So I want to make that note as well. From this picture, it should be clear that S has to be a subset of the closed interval that starts at the infimum and runs up to the supremum. It is a closed interval because there's nothing inside the definition of infimum or supremum that prevents them from being inside the set S. We can go back and add one more thing. If the infimum is not part of the set S and the sup is also not part of the set S, and let me clean up my notation there. So if sup is also not an element of S, then it would turn out that S would be a subset of the open interval that runs from the infimum to the supremum. But obviously, if either the inf or sup is part of the set, then we have to look at a closed interval before we get a subset.